Hey everyone. I thought I would go over the test again. I got a lot of positive feedback last time from people kind of seeing how to work through test number one. And I thought there was a lot of positive stuff about it. So I was really glad I did that. And because of that, I thought I would do test number two. In fact, there's a couple of reasons. I won't list them all. But because and a big one is I'm short help, but another one is I just thought it would be more educational than a lab itself. And another one where the chancellor was asking us to do things that would be just a little different than a normal face to face, that might be more educational and less stressful and less requirements of the students. Anyways, and I said I wouldn't list those reasons. There's some others, but I want to just run through the exam, and this will be our lab today here. And so our lab after the test will be kind of you going through, and this will give you a chance to kind of self grade you. And when you do get the test back or you see your score, now you can go through and you can look at and you could probably see in detail what went wrong, and that worked well last time. So let me jump right in here. All right, so let's start with problem number one. Problem number one says, when a star undergoes a supernova explosion, its total energy is, and of course you probably recognize this right from chapter 7. This is the conservation of energy statement in itself. So the answer would be A, does not change. And so I'll put a right there. Does not change. Conservation of energy. In fact, I think these first 5 are all from that chapter 7. Here it says, if a sports car with a mass of 1,000 kilograms traveling down the road at 30 meters per second, its kinetic energy is. And this is just straight the formula for kinetic energy. This would be a 1/2. The mass would be 1,000. The speed would be 30, and you would square it. So 3 squared is 9, so that's 900. This would be 900,000. Half of that is 450,000. And so 450,000 would be C. Number 3, again, more energy. Under what conditions is kinetic energy conserved in a collision? And so if you remember from the lecture, I tried to emphasize, and I'll say it again, there is no such thing as conservation of kinetic energy. It's conservation of energy. And so when two things collide, there could be heat. So nobody would say for sure that the kinetic energy before is equal to kinetic energy after. But this one, it's saying what if it is. And so I guess one thing is there would be no heat. Now, it doesn't look like that's one of the options. But what it does look like would be the answer. And I'll rule out A, it is always conserved. No, kinetic energy is not always conserved. And so read that one carefully. Energy is conserved, but not always kinetic energy. But there's a special name for that, and so this collision is called elastic. And so that's the elastic collision. And so the answer would be B here is what we would say. We'd say that it's an elastic collision. These other ones really make no sense either. But I could see how you'd be tempted for A. But again, kinetic energy is not conserved. Oh, here's a pretty tough one. Hopefully this one didn't catch you off guard. It says a tennis ball at the end of a string travels in a horizontal circle at a constant speed. The circle has a circumference of 2 meters. The ball has a speed of 3 meters per second, and the centripetal force is 1.5 newtons. How much work is done on the ball each time it goes around in a circle? And there's 2 important clues here. This is, of course, the idea of work. Work is force times distance. But there was a little caveat in here, which makes it one of the harder problems on the test, is it has to be the force in the direction it moves. And so if you draw a little circle here, and you remember our little diagram from the board, that if an object is moving this way, a force in the direction it's moving would make it go faster, and a force opposite to the direction it's moving would make it go slower. and it's the force that is perpendicular. And that's what's going on this problem. We've got a force that's perpendicular. A force that's perpendicular would make it turn. And since the definition of work is the amount of force in the direction it moves, so it moves in a circle, but the force is perpendicular to that. So there is zero force in the direction it moves. So this calculation would be 0 times the distance, and one revolution would be 2. But 0 times 2 is 0, so you're going to get an A there for the answer, and that's could have been easily overlooked. The other kind of clue here is we also said work changed the kinetic energy, made it go faster or made it go slower. And the very first part of it says a tennis ball at the end of its string travels in a horizontal circle right there at a constant speed. Well, as soon as you said constant speed, you would know there's no work, because the work energy theorem clearly says any work that's done changes its kinetic energy. So in other words, it either makes it go faster or slower. That's why a force this way, which makes it turn, doesn't do any work. So yeah, that one could be a hard one. Hopefully you got it. 5. Watch the units on number 5. Again, I could see how this one could be done incorrectly here, because it says here, if a hairdryer is rated at 1,500 watts. Well, the first thing is to realize power is energy per time. Okay, so here it says how much energy does it do. Okay, so energy would be power. Let me just use P for power and T for time. So you want to multiply those two together. However, this also takes us way back to chapter 1, because a watt is a joule per second. So for this answer to come out in joules, and you can see all of our answers in joules, your time would have to be in seconds in order for that to cancel off. So let me take the 5 minutes and multiply it by 60 seconds in a minute. So this is going to be 300 seconds. That's going to get the seconds to cancel off and get us an answer in joules. And so if you're not careful, you could have messed up the units. And so even if you remembered the definition of power from this chapter, you might have messed up the unit part from this chapter, which is the watt, and then the watt, taking us back to the chapter 1. So 3 times 15 is 45, and then 1, 2, 3, 4 zeros. 1, 2, 3, 4. So 45 and 4 zeros is D, and so number 5 is D. In the next chapter, this is where we get into the rotational chapter, chapter 6. It says, Newton's first law of rotation states that an object will maintain a state of rotational motion unless acted upon by an unbalanced or even net, whichever word you want to put there. And since we're talking about rotations, it would be forces, not torque. I'm sorry, I said that backwards. It would be torque, not force. And so this Newton's first law of translational motion, as we learned in the first test, said unless an unbalanced force. And so then when we got into chapter 8 here, we said that we're going to use the word torque for things that make it rotate. And it was more than just semantics, although it is semantics, and so that's kind of what we're just doing here, that the answer is a different word. It's not force, it's torque, but torque is different than force also, so careful with that one. 7, again, another rotation. You might even remember me doing this one in class. I took a solid black disc and a black hoop. They had the same mass and the same radius, if you remember those two. And I rolled them down the incline, and I had them race. And if you remember, the disc won. And the argument was that it was harder to get the hoop to rotate. It had a larger rotational inertia. I spent a long time trying to point out that this is a bit difficult to get across to students, and I think even more so remotely, that the rotational inertia is not just how much mass, although that's part of it, but it's also where it's located, and the further out, it's harder and harder for it to rotate. So the hoop has more of its mass out further. And so this one just says which has a larger rotational inertia. And so again, as we raced it, we saw it was the hoop here, and so it would be A there. So number 7 is an A. All right, well, let's go to the next page. The next page, starting here with number 8. Number 8 says we have 2 flywheels. Now, you may or may not know what a flywheel is. That really isn't all that important. But I hope you get from the rest of it that it's an object with mass that's rotating, right? It says 2 flywheels have the same mass, but one is thinner than the other, such that its radius is twice that of the smaller wheel. If both flywheels are spinning. So there's really the key. And a flywheel is an engineering term for a big... not necessarily physically big, not because it's really big in its rotational inertia, and so it spins. And so once it's spinning, it wants to keep spinning, or to get it to spin is kind of hard. And so it's used to stabilize anything that's rotating, so it doesn't all of a sudden rotate a lot faster or rotate a lot slower, especially if you have these impulse pushes on it. So flywheel is very common. All your automobile engines, of course, have flywheels because the gasoline ignites once every 4 strokes, and so it goes boom, and then it spins around twice, and then boom, and spins around twice, and boom, and spins around twice. So the idea is every time it goes boom, you don't want it to go fast and then slow down. You want to kind of level that out, and so just throwing a flywheel is a good and easy answer to that. All right, well, I digress to what a flywheel is, but like I said, you don't really know what a flywheel is. But hopefully what you get out of this is that there's 2 of them and you're comparing them, and it says if both flywheels are spinning about their axis at the same rate, which one would be harder to stop? And so that's indirectly saying which one would have the larger rotational inertia. And as I explained on problem 7, the one with the weight further out. And so they have the same mass, but it's more than mass, it's where the mass is located. So the thinner one, it's got to be thinner to have the same mass, then which has its mass with twice the radius would be the harder one. And so the one with the larger radius. And so number 8 would be A there. Again, here's another rotational inertia. Well, it's rotational inertia and angular momentum. It says the reason that a figure skater spins slower as he extends his arms out is because... And maybe you remember me on the stool pulling my arms in and out and changing my rotational speed. And the argument was that the principle is called conservation of angular momentum. I keep that the same. And the angular momentum, which we called L, had the rotational inertia and the angular speed. So if this one stays the same, but the moment of inertia changes as I move my arms out, in this case, if I put my arms out, then the angular speed is going to go down. And so let's see what the answer would be. Experiences the small torque. No. His angular momentum is greater. No, not that one at all, right? His angular momentum is less. No. His rotational inertia is greater. Yeah, so his rotational inertia went up. And also, because his angular momentum stayed the same, and that's not listed here, his angular speed would go down, and so the reason it's going to spin slower, right? So I guess our best option is right here. His rotational inertia is greater, so that'd be D. Like I said, definitely not B or C. Don't fall for that one. Well, and then don't fall down. That's the first one now, right? We don't need any torque for this. We just keep spinning around. All right, well, then 10 says, assume that Jerry sits on a freely rotating stool. Oh, and hopefully, again, you remember me doing this one. Sitting on a stool, freely rotating, holding a bicycle wheel with its axis in a vertical position so that it rotates in a clockwise direction when viewed from above. Now, let me pause right there. So it sounds like to me what we have, there's 2 objects, Jerry and this wheel, and the wheel's already spinning, and the wheel's already spinning in a clockwise direction. And so if Jerry turns the wheel over, he will. Now, the key again is this is conservation of angular momentum. And before Jerry turns it over, we've got an angular momentum that's in a clockwise direction. An angular momentum has to be conserved, so it's always going to be in a clockwise direction. But when you turn that wheel over, so you kind of hold it like this and you turn it over, the wheel itself is now going counterclockwise. So that means something has to go not just clockwise to make up for the counterclockwise, because that gets you back to zero, but then even more so clockwise. And that would be Jerry himself here. So if Jerry turns the wheel over, he will not rotate. No, that'd violate conservation. Not rotate. No, that would also violate conservation of angular momentum. This sounds it. Rotate clockwise because his angular momentum is conserved. Yep. Rotate counter. No. So there it is. C. Well, then on to chapter 11 here. It says, which of the following is a compound? And so if you look at that periodic table, you'll see all these are in the table. These are all elements. This is the compound. This is the one that I used as an example of a compound. It's two things or two elements hooked together. And so H2O, hydrogen and oxygen. Given that carbon atom has a mass of, now this is good. This is that atomic mass number that I was saying. There are three ways to interpret that number. So if they said the atomic mass number is 12 AMUs, then the three things it means, I'll start with the easy one here, is that one atom of carbon has a mass of 12 AMUs, 12 atomic mass units. And that's what they say. So they're really telling me the atomic mass number. That also tells me it has 12 nucleons, and it also tells me, and this is what's going to be important for this problem, that 1 mole of carbon atoms would weigh 12 grams. Okay, so the question is this: how many carbon atoms are there in a diamond with a mass of 1 gram? So I'll say it again, the 12 AMUs is its atomic mass number. Now, its atomic mass number would say that, I would have 1 mole if I had 12 grams. Now, I don't have 12 grams. I only have 1 gram. So I guess they're saying I have 1/12 of a mole. That's what they're saying. And 1/12 of a mole, and a mole is 6.02 times 10 to the 23rd. So maybe I'll pull in the calculator for this. 6.02 times 10 to the 23rd and divide it by 12. It looks like I got 5.02 times 10 to the 22. 5.02 times 10 to the 22. So that'd be B for number 12. All right, good. Again, chapter 11 here. The pressure that a gas exerts on the walls of a container is a direct result of, and this is those bouncy BBs you saw me in the videos probably 1,000 times playing with them, and they're bouncing around and hitting off each other. They make a pressure because they ricochet and they hit the walls. So that's the pressure. Repulsive force between the gases? No, it's not an interaction of the gases. It's an interaction of the gas and the wall. So definitely would not be A. Volume, that's not a pressure. And D, both of those, reading them makes no sense. It's the mass of the gas, the volume of the gas. So let me just read C. It sounds like that must be it. There it is. Collisions of the gas molecules with the wall. Yep. So 13 is C. 14, again, more question about pressure. The pressure in a container filled with the gas increases when it is heated because, so again, kind of going back to here, the pressure is caused by this collision. Now, heating, if you probably heard me say a million times, this is where our thermal expansion come in. When you heat something, you make the molecules jiggle faster. So they're going to have more motion to them. And that motion is going to hit the walls, or that greater motion means each one is going to hit the wall a little harder. So the walls do work on the gas. No, work is force and distance. The walls didn't even move. That makes no sense. The average momentum of each gas particle. Yeah, there it is, the motion. Now, they didn't say speed. They said momentum, but that's it. Maybe I should better check the other one here. The number of particles, no. Of course, increasing the number of particles would have increased the pressure also. But that's not why this question. The pressure is increased when it is heated, not because there's more particles, but they're moving faster. the volume of the gas decreases. No, that would be like A. There's no movement to the walls. Okay, good. So they use the word momentum here, but either way, there it is, B. And so 14 would be B. Last one here from chapter 11 says, what happens to the temperature of an ideal gas? What happens to the temperature of an ideal gas if its volume is reduced to half while holding its pressure constant? All right, so let me just write down PV equals to nRT. That was an important equation we worked out. And I was saying a good way to look at this is to put the P, the V, and the N, and the T maybe on one side, because that all equals the ideal gas law. So if you call that its initial conditions, that would same constant, so we don't have to even worry about the constant, would be the same after we did whatever we did. So this equals that. And so it says, what happens to the temperature? So we're looking for this. What happens to the final temperature? What happens to the temperature of an ideal gas if its volume is reduced? So we're going to change the volume to half while holding its pressure constant. So the pressure constant means it is the same value on both sides. And the fact that it says a gas, and so we're talking about the same number of molecules, and so I really have something that looks like this, that the ratio of the volume over the temperature before I do something is the same as the volume over the temperature after I do something. All right, so now back to the problem. What happens to its temperature? Okay. And here, what happens to the temperature if we take the volume and cut it in half? So in other words, this factor here, we're going to reduce by a factor of 1/2. So to keep the same ratio, oh, I guess I shouldn't have put it there. I should write it this way. It would be 1/2 of the initial. And to keep the ratio the same then, this must be 1/2 of the, initial also. If you, in other words, if you reduce the numerator, you've got to reduce the denominator by the same amount. I suppose another way is just to leave this as final temperature and then cross off the initial one and then cross multiplied, so you would get final temperature. When you move it over to here, you would still have the 1/2, and then you would have half the initial. But no matter how you care to work out your mathematics here, we clearly have an answer that says the final temperature is 1/2 of the initial. So cut in half is the answer they want. All right, so done with the second page, and I think we're on to chapter 12 here. Okay, so chapter 12, number 16, which has a larger density, a gold brick or a gold coin? Well, they're the same. They're both gold, and be careful with, total mass and total volume as opposed to density. So that's why I bought those big bricks I was trying to show you. Here's Archimedes Principle. Tells us that the buoyant force is equal to, and I said it a number of times, I'll say it again. Archimedes Principle says the buoyant force is equal to the weight of the displaced fluid. So it looks like A and C says the mass of something, so I'll just cross those out. No way those are in. This is the weight of the object. No, it's not the weight of the object. If it was the weight of the object, nothing would ever sink, right? The buoyant force would equal the weight of the object, and that force would be 0, and nothing would sink. But this is it. It's the weight of the displaced fluid, the fluid that would have been there. That was, of course, going back to the lecture, that was his whole argument, Archimedes' argument, that, what would have been there if that object wasn't there would have been the fluid itself. And that fluid would have stayed there. So that buoyant force must be equal to the weight of the displaced fluid. This is a good one. And actually, 18 and 19 go together here. But the salt water is slightly denser than fresh water. I think I said that a couple times in the lecture, and I know we measured it in the lab. Oh, in fact, this is a homework problem. A 50-ton ship will experience a greater buoyant force when floating in a lake of freshwater, saltwater. The buoyant force would be the same. It'd be the same. It's got to be the weight of the ship. Now, it would look something like this. If this was freshwater and I drew kind of the cross-sectional view of a ship, maybe, if you'll let me do that, maybe this would be the ship as it was floating in, say, freshwater. And it would be displacing this much. This is the water line. And so this is how much is below the water. But I do know from Newton's first law that the net force has to be zero. The boat is not going up or not going down. So it's being pulled down by gravity, its weight, and it's being pushed up by the buoyant force. So I know those two have to be equal. And anytime the ship is floating, so if we put it in salt water, so here's the salt water. We still got to come up with a net force of zero because, again, it's going to float. And so gravity pulling it down and buoyant force going up is zero. The thing that could be different then, and would be different, is that the boat would not have to displace as much water in order to get a buoyant force. Because remember, back to this one, the buoyant force is equal to the weight of the displaced fluid. So the boat would float higher. But that's not relevant for the question. What's relevant for the question right here is that the buoyant force would be the same. It would be whatever the ship weighs, which is the 50 tons. So both of these, whether freshwater or saltwater, would displace 50 tons of water. You need a larger volume of fresh water to make 50 tons than you do of salt water, but the force would be the same. So there's C. And see, that goes together with 19, which says here, then salt water is slightly denser than fresh water. And then it's talking about a 12-pound bowling ball. And a bowling ball will sink to the bottom. And they even say here it's at the bottom. But it says, will a 12-pound bowling ball feel a greater buoyant force sitting on the bottom of a freshwater lake versus the ocean? Now, the ocean's saltwater. But in this case, if I draw the freshwater with the bowling ball at the bottom and the salt water with the bowling ball at the bottom, both of them are displacing the same volume. And so it's a little different than 18 where they were floating. And so it's the same volume, but the same volume of salt water would weigh a little bit more. That's why they said it was more dense. And so the buoyant force is equal to the weight of that displaced. And so it's going to be the salt water, so on the bottom of the ocean. And so 19 would be B. 20. Which of the following is not, I'm glad it's capitalized there, these are always tricky questions, a Bernoulli effect. And the two I see right away that we did in class was the curveball, right? We talked about, when you had a ball and if it was, let's say, traveling this way, but let's say it had a top spin like that, so maybe like a hit tennis ball. As it goes forward, it would hit the air molecules. The air molecules would be pulled underneath it because of the spin. There's where you would have a high speed. This would then be a low pressure. You'd have a high pressure above it. Anyways, this curving of a ball, whether it be sideways or up or down, is because of the spinning of the ball and the aerodynamics, and definitely from a Bernoulli effect. So we talked a lot about that one in class. We also said that's the idea of an airplane wing. The shape of the airplane wing makes the air on top of the wing go a little bit faster than below, and so therefore we have the reverse effect of this, where we have a low pressure on top. The raising of the tarpaulins on a moving truck is actually a Bernoulli effect. Your author talked about it. I don't recall me exactly talking about it, but and nobody actually uses the full word tarpaulin anymore, but a tarp. So if I drew a pickup here, and I put a I wonder if I can draw a little more three-dimensional, boxy-looking truck here. But if I put a tarp across the back here and was driving down the road, the wind would blow like this, and it would be a low pressure. And so just like this baseball, the tarp tends to bow upward like that. You see that in convertibles really well, too. The passenger area just kind of folds up, and it kind of inflates upward really big when the car is driving. So that is a Bernoulli effect too, the rise of the tarp. And of course, this we talked about floating objects already many times. That is an Archimedes principle. So hopefully you saw that one and said, "Oh, well, that's an Archimedes," even if you didn't completely understand A. And hopefully you saw B and C. So the answer would be D for number 20. And then finally, the last four. This is our chapter 13. It says here, a calorie is defined as the amount of heat required to raise the temperature. And this was just the definition, right? It's a metric system here, 1 gram by 1 degree Celsius. So it's not a pound, that's the BTU. It's not Fahrenheit. Again, it's 1 gram of water, 1 degree. And so there's a B. How many calories are then required to heat 600 grams of water from 23 degrees Celsius to 33? This is just kind of a straight plug-in equation of the heat is MC delta T, which you saw me do this many times. So in this case, it's 600 grams. You would have to go back to the definition of what a calorie is. That's the specific heat of water, 1 calorie per gram per degree Celsius, times 10 degrees. And the units cancel out perfect and come into calories, and that's what it's saying, how many calories, okay. And then it would be 600 times 10, that's 6,000, so it looks like C would be the right answer for that one. 23 here says, why do climates near the coast tend to be more moderate than those near the middle of the continent? And I talked a lot about Santa Barbara. And let's see, there was a couple of reasons. Let's see which one would be the correct one here. The water has a relatively high specific heat. Yeah, that was part of it. There's a bunch of other things that go into play, so I better read all of them. But this is a big one, right? That sun shines, and I was talking about in class how if it shines on the water, because this number is so big, it'll barely warm up the water. But as it shines inland, then it on the rock and the sand, and so that's what the middle of the continent is saying. The rock and the sand, they're going to warm up like really, really quick. And so your sand and rock, which then warm the air, it makes it hot, whereas the water doesn't warm and then cools the air and then keeps it cool then in the summertime. Water has a high latent heat. True, not really important there. Because the coasts have lower elevation. True, not really important. Because it rains a lot along the coast. True, sort of. If you compare it to mountains, no, because the uplift can be more rain than the close water. But yeah, the coasts in general get more rain than inland, although it can get squeezed out by mountain ranges. So mountain ranges usually get more precipitation than the coasts. But either way, it's maybe true, but again, not relevant. So anyways, 23 is A. And then the last one of the multiple choice, before we get on to the free response, says, which of the following is not, a method to transport thermal energy? And so if you remember at the end of 13, I said there was the conduction. That was the first one we did, the bumping together. The convection, that's the actual movement of the molecules. It was a combination of thermal expansion and Archimedes Principle. And then the radiation. And so we talked about the sunlight, and we did that little experiment with the black and silver test tubes. So the one that's not is the condensation there. And so there's page 3 and the answer to the multiple choice questions. Now let's go to the free response. And they'll kind of go back in the same order. The first 2 will be on energy, coming from chapter 7. Here it says an object is dropped from 75 meters. What is the speed of the object after it has fallen 35? Now, there's 2 different numbers here. I suppose if you're not careful, this could throw you off, but this is a conservation of energy. The gravitational potential energy, mgh, is then converted into its kinetic energy. But I would say a little bit of, need to be a little careful with this H, because there's 3 H's I see up here. Here's the ground. The first H is the 75, that it starts above the ground. The next H is the 35, that it actually fell. And then another H that would fit here is the 40 that still remains. And so which of these would be the appropriate H here? Oh, did I get that in the picture there? So there's these three different H's, but the H of relevance here is the how far it has fallen, 35. So after it has fallen 35, so the 35, would be the loss of potential energy. It goes to the kinetic energy. In fact, we can even simplify this with one step by saying there's a mass on each side. In fact, we must, because we don't even give the mass of the object. So if we bring the 2 over to here, we get a 2, we get a G, we get an H. That would be the V squared. So then if we take the square root, we would get just the V. So if we grab a calculator then and go 2 times G, 9.8, or 10, you can do 10, that's fine. And then the 35, and then take the square roots. 26.2. So 26.2 meters per second would be the speed. And it would be a little higher than that if you use the 10, which is fine. Number 26. Here we have a force of 44 newtons is applied to a 4 kilogram object. Moves at a distance of 4 meters. If the object starts from rest, what is the speed of the object? So this is that work energy theorem we kind of mentioned earlier, that the work done on it would go to the change in the kinetic energy. And the kinetic energy is 1/2 mv squared. So maybe that's my starting point. Something that a few of you emailed me there, and good, I'm glad you did. Was the force in the direction it moved? And it's not as clear as maybe it could be, but the important thing is the object starts at rest. So right there would tell me this term is 0 because the initial speed is 0. But also what it would tell me, if the object was already at rest, it would only move in the direction of the force. So yes, the force and the direction it moves is in that same direction. So it's, again, at rest, and I push it that way. It moves in the direction I push it. It's not like it was already moving. Like if it was already moving to the left and I push it to the right, well, then it would be slowing down. I guess that would still be work, but if it was already moving, I could push it perpendicular to the direction it's moving. But I don't have that option here. So it was a good question. I'm glad a number of you emailed me, because it does go back to that tennis ball problem in the multiple choice. But this can't happen. The way this is worded, it has to be moving in the direction it is pushed. So I can clearly say that the force is 44 newtons, and the distance that it moves is 4 newtons, and they're in the same direction. So then I can put a force of 4 kilograms here and get a final speed squared with a speed of 0. And so the final speed is, and I probably going to need a calculator for this, Looks like this comes to over here and becomes 88 for the square of the speed. So the square root of 88 is about 9.38. So 9.38 meters per second is the final speed. So again, those two from Chapter 7, Conservation of Energy. This one here, again, rotation. Looks like this is an angular speed one. It says if a wheel on a car accelerates from rest, okay, keep that in mind, at a constant rate of 2.7, and watch your units, this is revolutions per second squared. How fast is it turning after 2.5 seconds? Okay, well, the definition of angular acceleration was a lot like the definition of translational acceleration. And it looks like in this problem, they've given me the angular acceleration and the time. So the angular acceleration is 2.7 revolutions per second squared, and the time is 2.5 seconds. If I grab a calculator, 2.7 times 2.5 is 6.75. 6.75, and if you look at the units here, this seconds would cancel with the one there. Revolutions per second. And it doesn't tell me I need to change any other kind of unit, so I won't go to radians or degrees or anything. So I think I'm done, almost. I suppose I should be careful that I have really just calculated the change, which would be final minus initial. But they also say in here it starts from rest, so that I know the final and the change are the same, because it starts with a 0 there for the initial. So that is an important part. And so I guess I could just put down here, this is the final speed. So the change in the speed and the final speed are one and the same because it started from rest. Another rotation one here is a 2,200 kilogram car traveling at 20 meters per second around a curve of radius of 45 meters. What is its angular momentum? And so one of the things covered in that very long chapter of 8 was the equation for the angular momentum was its mass, velocity, and its radius. And we use the symbol L. And this is just a straight plug and chug. They give us the mass, 2,200 kilograms. They give us the speed, 20 meters per second. They give us the radius, 45 meters. And so now I can just grab my calculator, 2,200 times 20 times 45. And it looks like I've got 198 and 4 zeros. So 198,000,000. If I put in my commas so I can read it a little better, okay, so that's 1,980,000. And if you look at the units, this is a kilogram, there's a meter squared, and it's per second. And also we don't have a name for that, so I can't call it anything. I just need to put it just like that into the answer. So there's the answer. Moving on into chapter 11. I did a good one in class on how many atoms based upon size. And so this is the same idea. It says how many atoms are on the surface of a rectangular beam. So I'll just draw a rectangular beam. And it says it's got a width of 10 centimeters and a length of 4 meters. So maybe the first question I will ask is how many atoms would fit along here? And that means the big piece is 10 centimeters and the small piece is the size of an atom. So that's what, if you recall from the lecture, I was trying to point out here, what's the, how many of these little things fit into those things. That's why you learn division in 4th grade. And the thing to remember then for this problem is the size of the atom. And so notice it doesn't say what kind it is, because that was our whole point. It doesn't matter if it's aluminum or gold, they're roughly about the same size. And so you can just figure out how many fit in here. So this would be 10 to the minus 2 meters, and this would be 10 to the minus 10 meters. The meters would cancel out. I'd bring this to the top and add. And so it looks like about 1 times 10 to the 8th, which is 100 million atoms, would fit along this line top to bottom. And the same thing over here, I could take the big length, 4 meters, and divide it by the size of the atom, 10 to the minus 10 meters, to see how many atoms fits along a row. And then the meters cancel off, and you're left with 4 times 10 to the 10th. So you can now then say I have this many in a row and this many in a column. And so if you wanted to ask how many total do you have, you take the number in a row times the number in a column. And so this would be 4 times 10 to the 18th. Yay! So that's how many would be on the surface of this being. Nice. And so again, from chapter 11. So going on to the last page here, the last 5 free response, and the second one from chapter 11 here, says that we have 8 liters of an ideal gas. It's heated from 19 degrees Celsius to 150 degrees Celsius in a container with a fixed volume. Oh, keep that in mind. Its initial pressure is 101 kilopascals. What is its final pressure? And so earlier, and I'll just repeat it here, I like to write the ideal gas law instead of PV equals to nRT as PV over NT equals R. Because I can call this initial, 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 and initial. And then when something changes, I'll have a final pressure, I will have a final volume, I will have a final number of molecules, and I will have a final temperature. And so I know that these 4 initially have to equal these 4 final, and I don't have to mess with what R is. And a big part of this said a fixed volume. So even though they said 8 liters, it's kind of irrelevant. This volume here, which is 8 liters, would cancel with that volume there, which is 8 liters. So don't even need the 8 liters. And again, they say an ideal gas, and so, they don't say that we, add more molecules or take any away. And we don't seem to ever do any problems like that. That's important physics, but it's more about chemistry at that point where you have a reaction and you change the number of molecules because, maybe the reaction then, as the reaction takes place, and so, A and B react with C and D, and maybe that forms 1 molecule out of that. So 2 molecules now become 1 molecule. And so the number of molecules could change in a chemical reaction. It could also change if we just added more in or took some out. But like I said, that's not a normal process for a physics discussion. So we're back to this that just says the initial pressure over the initial temperature then equals the final pressure over the final temperature. And that's the one we have to work with. The initial pressure is the 101 kilopascals. And here's a very, very, very important step. Really what could throw this problem off right here is, remember we said temperature must be done in the Kelvin scale, right? This equation only makes sense on the absolute scale. It's the only one where 0 pressure would correspond to 0 temperature. That was the neat thing about the Kelvin scale. It's the only scale where the numbers on the temperature scale correspond to the motion, and the pressure corresponds to the motion. So this must be done with the Kelvin one. So keeping that in mind, this 19 Celsius needs to be converted to 292 Kelvin, because that's 273 plus 19. And when you add that together, you get 292. And then the same answer or same discussion for the 150. I need to take the 273 and add 150 to it. And so that's going to give me a 423. 423, yeah. And then I can solve for final pressure. All right, so grabbing my calculator, maybe I'll do this side first here. This is 101 divided by 292, and then move this over times 423, and I get 140, I'll just call it 146, and we're in units of kilopascals. So it's 146 kilopascals. On to chapter 12, and again, 2 from chapter 12 here. Here we have a 12 cubic centimeter block of aluminum. I don't know if I need to draw a picture, but I'm kind of thinking I will. So I got a picture here. Here's my block. It's got a volume of 12 cubic centimeters. Okay, so 12 cubic centimeters block of aluminum. Oh, they give me the density of aluminum. I don't know if I'll need that. It's lowered carefully into a completely full beaker of water. Okay, so maybe right here I have a beaker of water that's exactly full to the top. And so clearly when I put this in, it's going to displace the water. It's going to lift it up. It's going to flow over. And this says, what is the weight? Ooh, weight. That's interesting. Of water, and in newtons, so there's my units, that spills out of the beaker. Well, okay, so I guess the important thing here, and I guess I do need this density, is to realize that this piece of aluminum is going to sink. Remember we said anything that is more dense than the fluid it's in, it would sink. That was the result of our discussion about Archimedes' principle. So when I put this in, it's going to look something like this. This is going to sit down at the bottom now, because aluminum, having a density of 2.7, is greater than the density of water, which is 1. And you probably even didn't need to know that aluminum sinks. But, all right, so I put it in there, and I need to know it sinks to the bottom. But the key, then, is this piece of aluminum sitting at the bottom, which has a volume of 12 cubic centimeters, is going to then displace 12 cubic centimeters. And so what ends up happening is a volume of 12 cubic centimeters spills out the side. And I'd be done if the problem had said, what is the volume? But that's not what it says. It says, what is the weight? So maybe I need to remember that the density is mass over volume. And I do have the volume at 12 cubic centimeters. And the density of water is 1 cubic centimeters. And that then would give me the mass of the water that spilled out. Now, I suppose an easy mistake to make here would be to put the density of aluminum right there. Don't do that. I'm not talking right now about the aluminum anymore. The aluminum was the first part of it where I put it in. But now I've realized that the volume of the water is 12. So I need the density of the water, which is going to give me the mass of the water. So I still won't be done because I need the weight of the water. But at least this will, water. Okay, so this is going to give me the mass, so density times volume. All right, so that's what this is. So 12 times 1 is just 12 grams. So you probably didn't even have to write out a formula for that, but maybe the harder thing is to realize we're talking about water here, the volume of the water and the density of the water to give me the mass of the water, not the aluminum anymore. All right, so what spills out, as I said, we know the volume is 12 cubic centimeters. We now know that the mass is 12 grams. And so then finally I can get to weight, and weight goes back to some earlier chapters. Weight is mg. But also to get it newtons, we have to have our mass in kilograms. So both of these are a few steps here. And this I don't know, this was quite a few steps. I'm beginning to wonder if this was I should classify this as the hard one. Maybe the hardest one on the test. But looking ahead, maybe I'm thinking that next one is. And anyways, there's the mass in kilograms. And then, of course, G is the 9.8 meters per second squared, or 10 if you want. That's not a big deal. So now I can get out my calculator and go 0.012 times 9.8, and that would be the 0.1, I'll just go 12 newtons. I should have circled it up there. All right, so there's finally the weight. And so there's quite a few steps there. Starting with the aluminum and getting to the water and realizing they're the same volumes, and that volume leads to the mass, and that mass leads to the weight. Huh. All right, well, I hope that one worked well for you. Let's go to 32. 32 here has a block of metal that weighs 19.6 newtons, is submerged underwater and onto a scale that reads 15.5. And then the question goes, what is the volume of the block? So yeah, this got a couple of steps in it too, but I'll start with the buoyant force, because this is what we were showing you with the rock and the aquarium, and also what I was showing you when we did the Archimedes lab, that if you subtract these two, what's the reading on the scale when it's in the air? Okay, there it is. And then what's the reading when it is underwater? Because the scale is really telling you how much the scale is lifting up. And the fact that it went down by this much, so it went down from 19.6 to 15.5, it went down because there was a buoyant force. And so it's the difference between those that is the buoyant force. So if we subtract these two, what are we going to get? 4.1 newtons. So, all right, so the buoyant force is 14.1 newtons. But what makes this a hard problem is it doesn't stop there. It asks for the volume of this block. Now, we've got to make the connection that this buoyant force came from Archimedes' principle. The buoyant force is equal to the weight of the water displaced. So the good thing here then, if I just put mg here, and then maybe I'll even point to it, water. Since this is the buoyant force on the object, because I weighed it, it must also be the weight of the water displaced. So this is the mg, the amount displaced. And so this, if we think about this then being displaced, and we go to solve this, this would be the m, the mass of the water that's been displaced. So why don't I try 4.1 divided by 9.8 would then tell me that 0.418 kilograms is then the mass of the water that's been displaced. And let me just take your attention back up to here. There's a direct connection between the mass and the volume and the density. And so I could then take this and bring it up to here, and maybe before I even do that, I'll just convert it to grams. So it's 418 grams, because again, coming back to this problem up here, this would be like the water that has been displaced. There's 418 grams. Well, that would correspond to 418 cubic centimeters then of water that has been displaced. And it's been displaced because it's the same volume of the object. And so this is the volume of the object. So the volume of the object is also the volume that has been displaced, because it is underwater. And there it is. Quite a few steps in that one. And again, I hope that one went well for you. That one might, yeah, I think that one's harder than that one. It used kind of a couple of the same things there. Well, then finally, I've been talking for a while, so maybe I should wrap it up here kind of quickly. But here is the chapter 13. This is just putting two things together. You might remember in class, I had an aluminum and a lead block, and I calculated their final temperature. This one is more of an example of what you did in the lab, where you took a piece of metal and you mixed it with a water. And, well, in the lab, you actually measured the final temperature and used that to get the specific heat of the metal. This is kind of the reverse then. This is giving you the specific heat of the metal and asking you to calculate what its final temperature is. So it is a little more like the one I did in class, although I didn't use water for my second object. I used aluminum and lead. This one has aluminum and water. But here's the key. It's conservation of energy. The Q that comes out of the hot one, and so it looks like the aluminum is going to be the hot one at 100 degrees. That's why, like I said, these numbers are pretty much a copy of the, well, the 100 degrees is a copy of the lab because we put it in the boiling water and we used aluminum. But our aluminum piece was bigger than that. Our aluminum piece was 90-something grams. So, and our water was a little more than that, and not quite that warm. But hopefully you see the idea. And then also, as I tried to emphasize in both lecture and lab, this is the absolute value of it. So this is the MC delta T, and I'll put absolute value, has to equal to the MC delta T there. Where I'll just say this first one is the aluminum, and the second one is the lead. No, sorry, the water. Lead was in class. So here's the mass of the aluminum. So here's the 50 grams. Here's the specific heat, 0.22 calories per gram per each degree. Here's the change in temperature. Now, I'll say it again. Normally, we do final minus initial, but noting that it's absolute value and that the aluminum cools down, let me put it as 100 minus final. So it's a positive number, and that's what the absolute value would do, because like I said, normally when you do change in temperature, you go final minus initial. So it would be final minus 100. But that would be a negative number. And so when you do absolute values, you have to switch the sign. So that switched the sign. If they're a negative number, you don't do anything. It's a positive number. And then this one here representing the water would be a positive number. So I don't need to change anything on it. Its mass is 23 grams. Its specific heat, since it's water, is 1 calorie per gram per degree. And its change in temperature would be final minus initial. And again, since it's warming up, that's a positive number. So taking its absolute value, don't do anything with it. So if I go 50 times 22 here, that's 11. So that's going to be 11 times 100 minus final temperature. And 23 times 1 is 23, and then this would be final minus 25. And maybe I'll move the 11 over here. So 23 divided by 11 is 2.09. So 2.09, and we'll have final temperature minus 25. And that's over here will just be 100 minus final temperature. If I do a distributive property here, this becomes a 2.09, and then that over here makes a 3.09 final temperature. This, on the distributive property, would be this 2.09 times 25, and so that there is the 52, I'll call it 52.3. But when I move it to the other side, I'd be adding 100, so this would be 152.3. So finally, a little crowded in here. So, I don't know, maybe this one is harder than that one. But again, hope this one went well for you. Let me take the then 152.3 and then divide it by the 3.09 and get 49.3. So 49.3 degrees Celsius is the final temperature there. But as I said in class, and say it again here, this is it right here, the conservation of energy. The hot or heat energy coming out of the hot one is equal to what goes into the cold one. And since we're changing temperatures, that's a specific heat question. So this is a specific heat question, really. Whereas this last one is got specific heat in it, but it's a little more than that because it also changes phase, and you need to recognize that. It says here, how much energy does it take to bring 10 degrees or 10 grams of ice at negative 10 degrees to 20 degrees Celsius water? And so I'm gonna write this as a Q, since it says how much energy, how much heat energy. But I'm also going to write this as a Q1, a Q2, plus a Q3. Because there'll be really three things that go on here. It's starting out at something less than 0 degrees. So hopefully you recognize it's a solid, it's ice. And so as it warms up, you would do a specific heat calculation, MC delta T, but it would be for ice. Then once you get to 0 degrees, the bonds are going to break, and it's going to be a latent heat of fusion. This is the part that it's trying to say it takes energy to break the bonds. And so you got to melt it. And that doesn't warm it up at all. It just takes some energy. So it's still now at 0 degrees. But then we've got to add even more energy once we break all the bonds and make it a water, and we warm it up to our 20. So I'll have another MC delta T. But this is when it's water. So this is when it's warming up as ice. This is when it is melting. And this is when it's warming up as water. Now, in all these cases, they're 10 grams. But as it says here, and we did in class, the specific heat then of ice is 1/2 of a calorie. And we would be warming at only 10 degrees, not 30, but just 10 degrees. Then, again, we would have 10 grams, and we would be melting all 10 of those. And there's the latent heat of fusion right there. And then now we've got that 10 grams, but now we've got water. And so the specific heat has changed to 1. It's no longer 1/2. Not even listed there, hopefully, because you realize it's water. And then, of course, now I'm going to warm it up 20 degrees. So 10 times 10.5 makes 50. 50 calories. 10 times... Did I do that right? Yeah. Okay. And then 10 times 80 is 800. And then 10 times 20 is 200. And all of these are calories. So 800 and 200, that's 1,000, and then 1,050. So 1,050 calories would be the total. All right, good. Well, I hope that went well for you.